We recently introduced the divergence and got some insights of its meaning, its interpretation, but we actually didn't apply this yet to anything. So let's look at the example, and a relevant example would be to understand what is the divergence of some electric field. Let's look for the electric field we already considered, which is the field generated by a single charge, point charge placed at the origin at point 0, 0, 0. So let's try to understand, if we know what is the electric field of that vector field, what would be the divergence of that vector field? So the question is, in mathematical terms, calculate the divergence of the vector field given by that expression, where q and epsilon 0 are constants. So how to do it? Well, again, we should use the definition, but before that, we remind ourselves that r is the distance from the origin, and it corresponds to the first component of the electric vector field. And we need to differentiate these with respect to x, according to the definition of divergence. And then we do the same for y and z. So let's start by differentiating this thing with respect to x. So we have the first component, the component ex of x, y, z, which is q over 4 pi epsilon naught times x multiplied by x squared plus y squared plus z squared to the power of minus 3 over 2. And if we take a derivative, we just use the product and chain rule, as you can see here, and ignore that constant because it's just a constant factor, so we can take it out. And according to the product and chain rule, we get first the one term and then another term. With the same expression inside the bracket, but to the power of minus 5 over 2 multiplied by 2x. And if we simplify it and write this with the common denominator, we will see that it becomes q over 4 pi epsilon naught x squared plus y squared plus z squared on one hand, minus 3x squared in another term, and the denominator is x squared plus y squared plus z squared to the power of 5 over 2. And if we simplify it a bit further, we will write it as q over 4 pi epsilon naught minus 2x squared plus y squared plus z squared over the same thing in the denominator. And if we make even one more step to simplification by remembering the definition of the distance, the r, we can write it as q over 4 pi epsilon naught minus 2x squared plus y squared plus z squared over r. Can you guess which power? Yeah, hopefully most of you realize that it is 5 in this case. So that is the expression for the first derivative, and likewise we can get the other two components, which have very, very similar form, except that they have minus 2y squared or minus 2z squared. And if we add all the numerators together, because they have the same common denominator, we will see that all of this is in fact cancel out. So it becomes identical to 0. And what it means? It means that if we'll take the divergence, which is the sum of these three partial derivatives, they will be equal to 0 at every point except for the origin, where things are special. But everywhere else, our divergence is 0. And that's not surprising. The reason for that is that there is actually an equation called the Gauss equation, which tells you that the divergence of an electric field equals to the volumetric charge density. And because here we have charge density is 0 everywhere except for the origin, that's exactly what we observe here. So we just verify that this equation is correct for a particular type of the electric field. Let's also look at some of the properties of the divergence. Again, they're somewhat related to the properties of the derivatives, because the divergence itself also is the derivative, but not a vector. So if you have two vector fields and a function and a constant, then you can show again a linear property like we've seen before, and it's also true for general vectors. You take two vector fields, take divergence, it's the same as to take the sum of divergences of these fields individually. You can take out a constant factor because it's ignored by derivatives. So it's again as a two linear properties. And also you can do similarly the product rule. So you can take a scalar function, which is a scalar field, and a vector field, and multiply them. The result will be a vector field. And you apply divergence to that. And according to the product rule, you'll find that it's the same as to apply the gradient of this scalar field, scalary product of them with the vector field, and then multiply this scalar field with the divergence of this vector field, and then take the sum of these two. So it is important to notice here that there is a gradient appearing as a result of taking divergence of the product of the scalar and vector fields. So this is I want you to bear in mind. So that is the gradient, and that is the divergence. And now you see they started to get some connections. And that is again the reason why it's so helpful to use that notation for the Nabla operator.